My name is Victor Gurewich. I'm a professor of medicine at Harvard Medical School and the scientific director of TSI, Thrombolytic Science International. Thrombolysis is the process of lysing or dissolving a thrombus, which is an intravascular blood clot. Since a thrombus is composed principally of fibrin, the process is also called fibrinolysis. A thrombus is responsible for most strokes and all heart attacks, the leading causes of death and disability worldwide. Eliminating an obstructive thrombus as rapidly as possible is critical. Thrombolysis or fibrinolysis is the simplest and fastest method, but how this is to be best executed remains controversial and is the subject of this presentation. This brings up a question. The body's endogenous fibrinolytic system utilizes TPA in combination with UPA, the other natural plasminogen activator. So why has TPA been used alone in therapy, especially since the endogenous system is ongoing, dissolving thrombi noiselessly without bleeding complications? Evidence of the efficacy and safety of endogenous fibrinolysis. D-dimer is routinely found in blood. It is never zero and averages about 200 nanograms per ml in normal individuals. Since it is the product of fibrin degradation by fibrinolysis, it means that fibrinolysis is ongoing. In the presence of thromboembolism, the D-dimer level increases by tenfold or more, reflecting the reserve capacity of endogenous fibrinolysis. This endogenous fibrinolytic system is free of bleeding complications and therefore provides a paradigm to be emulated in fibrinolytic therapy. This slide shows an important principle of fibrinolysis. Plasminogen is found free in plasma and also bound to its 3 receptors on the fibrin clot, and the latter is principally responsible for fibrinolysis. So I've shown that on the slide with the fibrin clot in the middle, the 3 plasminogens on the surface of the clot, and the plasminogen activator is represented by the green arrow activating those plasminogens. And it's those plasminogens converted to plasmin that are responsible for fibrinolysis. Activating the plasminogen in the plasma, which is surrounding the clot, does very little fibrinolytic work but causes a lot of side effects. Activating the free plasminogen in plasma has little fibrinolytic effect and causes degradation of clotting factors and bleeding complications. So the key to fibrinolysis is activating selectively only the plasminogens that are bound to the clot and leaving the other ones intact. Fibrinolysis is initiated by TPA, which is released from the vessel wall at the site of a clot to which it binds due to TPA's high fibrin affinity. TPA binds to a site on fibrin proximal to the binding site of plasminogen 1. As a result, a ternary complex is formed between the fibrin clot, TPA, and plasminogen, and this ternary complex promotes TPA plasminogen activation 1,000-fold. Without that ternary complex, or that fibrin promotion of TPA activity, TPA is a rather poor plasminogen activator. The fibrin degradation initiated by TPA creates 2 additional plasminogen binding sites. The different doses of TPA that are required to activate the 3 plasminogens, only one of which is specific for TPA, the one that TPA binds next to, and that requires only a 5 milligram bolus of TPA. But to activate the other 2, which are needed for fibrinolysis, an infusion of TPA is required of 90 to 100 milligrams, an enormous difference And this activation of these two plasminogens by TPA explains why TPA is both ineffective when used alone and hazardous. Evidence that UPA, the other plasminogen activator, is also essential is shown here. When the TPA gene was deleted in animals, little adverse effect was observed, whereas a UPA gene deletion induced spontaneous fibrin clot deposition. Deleting both genes caused extensive fibrin deposition in the animal. Therefore, both activators are required for a full fibrinolytic effect, and UPA, rather than TPA, is the dominant plasminogen activator. This slide begins after the initiation of fibrinolysis by TPA has created the two additional plasminogen binding sites, which are represented by the black triangles. The first of these, plasminogen 2, is on a special site called fibrin fragment E, FFE, which induces a conformational change in plasminogen 2 that enables the proenzyme form of UPA, pro-UK, to activate it to plasmin, which then activates pro-UK to UK, and UK activates the remaining plasminogen, completing fibrinolysis. And what the slide also shows is that there are two forms of UPA, the proenzyme form called pro-UK and the enzyme form called UK. And you get from one to the other by plasmin, which activates pro-UK to UK. But before that happens, pro-UK itself becomes a plasminogen activator in the presence of the conformationally changed plasminogen 2 related to its binding to the FFE binding site on fibrin. Therefore, pro-UK has two activities: its active enzymatic form due to plasmin activation and its proenzyme active form due to binding to the conformationally changed plasminogen 2. This is a unique form of pro-UK plasminogen activation. These sequential functions of the activators are analogous to those of a car. TPA is like a car starter in its function. UPA, being both a proenzyme pro-UK and an enzyme UK, is responsible for 2/3 of lysis and is like the fuel. Neither one can function effectively without the other. At fibrin-specific doses, only TPA can initiate lysis and only UPA can complete it. The activator's functions are independent but interdependent. They're also complementary. When they are combined, their fibrinolytic effects are synergistic. This was explained in the title of a published paper entitled The Complementary Modes of Action of TPA and pro-UK, by which their synergistic effect can be explained. The combination of TPA and pro-UK is synergistic in clot lysis. What is shown here is a clot lysis experiment. The clot is pictured on the left as a photograph of the clot, and on the right is the lysis curve that we've seen from that clot. And responding to 2 doses individually of pro-UK and TPA that alone induced 25% lysis, and when they were put together, we got 100% lysis. So that 25% lysis plus 25% induced 100%, which are synergy by definition, the definition being an effect greater than additive. Having discovered this synergistic effect by the combination, I decided to visit Genentech and show them the findings in an effort to put this information into practical use. The scientists in the R&D department received the findings with interest, but before leaving, the CEO thanked me very much for coming and said simply, "We hope you're wrong." A timeline is shown here. In the previous slide, we were in 1987. Fast forward to 2018, little has changed. Fibrinolysis and TPA remain virtually synonymous, and TPA remains the only activator in use. When UPA is mentioned in reviews, it is only in relation to its extravascular function for cell migration. A paradigm shift, as described by Thomas Kuhn, is needed, but this has evidently been delayed. But why? The problem with native pro-UK is that it is vulnerable to activation in plasma at higher therapeutic concentrations. Why that happens is shown on this diagram. The intrinsic activity of pro-UK at a higher concentration activates plasminogen to plasmin. Plasmin activates more pro-UK to UK, which induces a bleeding risk. In addition, plasmin also degrades clotting factor 1, which is fibrinogen, factor 5, factor 8, and 13. Therefore, a single-site mutant pro-UK was developed with a lower intrinsic activity that was stable at a 5-fold higher plasma concentration. And that's shown on this slide with a 5-fold lower intrinsic activity of mutant pro-UK, therefore a reduced liability to activate plasminogen to plasmin, plasmin to pro-UK activation to UK, and therefore a reduced bleeding risk compared to native pro-UK. On this slide is shown an experiment showing that mutant pro-UK, M pro-UK, spared hemostatic sites at fibrinolytic doses. In this experiment, TPA and pro-UK were compared for their fibrinolytic activity and their bleeding hemorrhagic tendency. Anesthetized dogs with transdermal abdominal incisions were infused with M pro-UK or TPA at equivalent thrombolytic doses. As shown here, bleeding from the transdermal abdominal incision sites was 10-fold greater with TPA than with M pro-UK. Therefore, to summarize, at equivalent lytic doses, M pro-UK caused 10 times less bleeding than TPA. Since in the natural fibrinolytic paradigm, the activator's function is sequential, a sequential administration was compared with a simultaneous one in vitro. Clot lysis was faster and more fibrin-specific with a sequential administration of the activators than a simultaneous one. The clot lysis curves are shown on the left, with the solid symbols representing the sequential delivery of the activators and the open circles the simultaneous. As shown, 50% clot lysis occurred in 72 minutes with the sequential delivery and took 120 minutes with the simultaneous. So the sequential was considerably faster. Similarly, 75% of fibrinogen remained given sequentially rather than 37%. Therefore, lysis was also more fibrin-specific. What this experiment shows is that the natural paradigm of sequential delivery of the activators is also more effective and more fibrin-specific. A final test was, does this sequential administration of the activators work clinically? We had an opportunity to test that in 1995 in a trial entitled the Patent Trial, in which a mini bolus of TPA followed by an infusion of native pro-UK was given to 101 patients with a heart attack with an AMI, acute myocardial infarction. This is the aforementioned Patent Trial. in which 101 AMI patients were given a 5 milligram bolus of TPA followed by a 90-minute infusion of Pro-UK. And the title page is shown here of the JACC publication from 1995. The essential findings are shown on this slide and are compared with the findings from the GUSTO trial, which was the best of the TPA monotherapy trials for AMI. As shown on the left, the TIMI-3 patency of the infarct artery was 60% in the patent trial in 90 minutes, and at 24 hours that had increased to 82%, representing continued lysis. By contrast, in the GUSTO trial of TPA, the 90-minute patency was 54% and went down to 45% in 24 hours, representing reocclusion. And corresponding to the better lysis in the patent trial, the mortality was only 1%, one patient out of 101, and was 6.3% in the GUSTO trial for TPA monotherapy. We became interested in the reason for the continued lysis long after the Pro-UK had been cleared from the blood, since its half-life is only 7 minutes. The explanation is on this slide, which shows that Pro-UK binds to platelets, and platelets, of course, have a half-life of 2.5 days, a good deal longer than the 7 minutes of the unbound enzyme Pro-UK. This shows a zymogram of platelets exposed for varying periods of time to Pro-UK. The unexposed is C for control, which have not been exposed to the Pro-UK at all, and there's still a shadow there, and that shadow is on the native platelets, meaning that this occurs in nature as well, because these shadowy-looking bars represent lysis of fibrin, which is what the zymography represents. These are lysis bands of platelets, meaning that there's a fibrolytic on the platelet. And in this case, under C, it's the native Pro-UK that is on the platelet. So this occurs also in nature. But starting with 0, this is the platelets that have been exposed to Pro-UK. Even at 0 minutes, that means as fast as you can pull them out, there is some Pro-UK already bound. But this increases over time, which is what's important with respect to the fibrolytic effect that we saw in the patent trial. This slide shows the uptake of Pro-UK by platelets. In this case, we used radiolabeled Pro-UK and exposed it to platelets in the presence or absence of a 50 molar excess of unlabeled Pro-UK. Therefore, we could sort out whatever non-specific binding there was, which is shown on the bottom of the slide. But the important finding from this slide was that the uptake of Pro-UK by the platelets reaches a peak at 90 minutes, which happens to be the infusion time in the patent trial. And we didn't have this information at the time that we decided on that time. But beyond 90 minutes, you don't get any further uptake, so there's no reason to give an infusion longer than that in order to maximize the uptake by the platelet. This slide, which shows zymograms, shows the uniqueness of this phenomenon to Pro-UK. Pro-UK is shown on the left, the uptake by platelets of Pro-UK. The next column shows low molecular weight plus Pro-UK, and you see the Pro-UK effect not diminished by the low molecular weight UK. Low molecular weight UK alone is not taken up at all. TPA plus Pro-UK is taken up. TPA alone is not taken up. This means that the platelet binding site is on the UPA-A chain, which is absent in low molecular weight UK and must be unique to Pro-UK, and that Pro-UK is the only activator that binds to platelets. And since this has an important fibrinolytic effect, this is a very useful property. The platelet phenomenon, which was responsible for the post-infusion coronary thrombolytic effect in the patent trial, was responsible for almost 30% of the total UPA lytic effect in the patent trial. The half-life, or the T1 half, of platelets is 2.6 days, and Pro-UK remains bound to the platelet membrane for their lifetime. The natural affinity of Pro-UK for platelets was responsible for the duration of its fibrinolytic effect in the patent trial and can be exploited in future trials. This is a clinically advantageous phenomenon which is unique to Pro-UK and M-Pro-UK. The results of the patent trial were unprecedented. Compared with standard TPA, the TIMI-3 patency of the infarct artery was almost doubled. No reocclusions were seen. 6-fold lower mortality than TPA was obtained. Had this regimen been adopted in 1995, when patent was published, almost 1 million deaths from heart attack could have been prevented in the US alone. No second trial was ever done because Pro-UK pharmaceutical development was discontinued. Conclusions. Only an activator combination, rather than monotherapy, can provide optimally effective fibrinolysis safely. A 5 milligram bolus is sufficient for TPA to complete its fibrin-specific fibrinolytic function. The bleeding risk of Pro-UK is minimized by the mutation. The endogenous fibrinolytic paradigm involves the sequential synergistic effect of TPA and UPA. Pro-UK's rapid and tight binding to platelets prolongs its fibrinolytic effect significantly and may make a 90-minute infusion optimal. The patent study validated the efficacy of the sequential synergistic combination. And finally, a TPA mini bolus followed by an M-Pro-UK infusion is expected to be sufficiently safe as well as effective to make more immediate reperfusion possible.